Hi everyone, welcome back to my video tutorial for weighted gene co-expression network analysis. In this tutorial, I'm going to show you how to perform the analysis and correlate the modules to the trait data and also identify important genes in each module. So first, let's note the library and also the data we analyzed in part 1 for the expression data, the trait data, and also the data that we analyzed in part 2 for the network data. So in part 2 analysis, we already got the module eigengenes. You can see here, if we click, you can see the data for the module eigengenes for each sample, and we have 19 modules. At the moment, the module eigengenes are named by the number. They are not related to the module color. So we can recalculate the module eigengenes with color labels. So let's calculate it. Now you can see we named it as MES0. We can have a look at this data frame. Now you can see the module eigengenes are associated with the module colors. So let's reward the module colors. Then we can calculate the association between the module eigengenes and the trait data. And also we calculated the p-values for the module trait association. Now we got the correlation values for each module associated with the trait data. We can have a look at this data set. You can see we have all the modules, 19 modules in the row names. And in the columns, we have the trait data information such as the weight, length, and the fat. And also we have a data frame for the p-value. You can see the data frame looks very similar as the module trait correlations. So if you just look at the values, it's really hard to see the strong or weak association between each module and the characteristic in the trait data such as the weight and the length. So we can make a heat map to show the module correlation value in the heat map. So we are going to show both the correlation value and the p-value in the heat map. So first we need to convert the data into a text matrix. Then we can set some parameters for the plot. Now we can use the label heat map in the WGCNA package to produce a heat map for the correlation and the p-value. Let's run the label heat map function. Okay, we got an error here, so we need to make this windows bigger. Then we can see the figure. Let's plot a heat map again. So now you can see we got the heat map. We can zoom in. So you can see we got the module names here and their corresponding color. And we have the p-value and the correlation value in the table. And we got the column names for the trait data down here. The important thing is that we color-coded the correlation value. You can see from -1 blue color to 1 as a red color. If we see a red color in the table, we know there is a high association between the trait data and the module. So for example here we see the highest value is 0.59 for the brown module associated with the weight. So from second part of analysis, we knew each module contains at least 30 genes, and we named the module eigengenes. Now we can continue our analysis to reveal gene significance in each module associated with the trait data. So because we see from here, the brown model has the highest associated value with the mouse body weight, so we are going to use the brown model as an example to do the analysis. So let's adjust our windows again. So first we need to get the information for the body weight from the trait data and create a data frame as weight. If we have a look at the data frame weight at the moment, you can see the column name is data trait weight, and we can change the name to just weight. Now you can see the weight data frame, the column name is named as weight. Because in our module genes data frame, we named the column name as module genes together with the color. And now we are going to calculate the gene significance and also the module membership. So we want to make some changes for the column names. So at the moment we can just keep the color name. Then we can calculate the gene module membership in the expression data. And also we calculate the p-values for the module membership. So you can see here, if we click the data frame, you can see we have the membership value for each gene in different modules. And also we have the module membership p-value for each gene in each module. You can see here the column name is still named as the module gene together with color. Now we can change the column name to module membership together with the color. And rename it as module membership together with the color. Let's run this code, and at the same time we also change the column name for the module membership p-values. We name it as p module membership together with the colors. So let's have a look at the data frame again. You can see now we changed the column name as module membership together with the color. The same for the p-values. You can see we changed the column names. So next we can calculate the gene significance in the trait data. We are going to calculate the correlation value between genes and the mouse body weight. And also, we calculated the p-value for the gene significance. If we have a look at the data, you can see we have the correlation value for each gene associated with the weight. And in the gene significance p-value data frame, we can see the p-value for each gene. But at the moment you can see the column name is weight. We can change the column name again to gene significance weight. And for the p-value, we can change it to the p gene significance weight. Now you can see, for example, the p-value, you can see we changed the column name. So now we quantified the module membership and also the gene significance for each gene. Then we can identify genes that have a high significance for weight, as well as high module membership in interesting modules. So we know the brown model has a high association with the body weight, so we are going to use the brown model again to plot a scatter plot using gene significance against the module membership. So let's get the module genes and the module colors for the brown model. Then we set some parameters again to make the scatter plot. Now we can plot the gene module membership against the gene significance, and we label the x-axis as the module membership in brown module, and the y-axis is the gene significance for body weight. And also we give the scatter plot a title as module membership against the gene significance. Let's make the scatter plot. Once again, we need to adjust my plot windows. Let's run the scatter plot again. Now we can zoom in to look at the scatter plot. You can see we have the gene significance for body weight on the y-axis and the module membership for the brown module in the x-axis. So from the scatter plot, we can see the gene significance is highly correlated with the module membership, indicating that genes are highly significantly associated with the trait, are also the most important genes in the module associated with the trait. Here we use the body weight as an example in the brown model. So if you are interested to analyze other model and different trait data, you can have a go to analyze it. So now we perform the analysis to obtain the gene significance and the gene relationship for the brown model associated with the body weight. So we can save the gene information for later studies. If we have looked at the column names for the expression data, you can see we only have the probe names. We don't have the gene information in the expression data. So we can get the gene information from the company that performed the microarray analysis for the data. They have an annotation file to show the gene name for each probe. Let's read the annotation data into R. Then we can have a look at the data. You can see in the annotation data, we have the probe's name in this column and the gene information in this column. So we can use the information for the probes and the gene name in this file to link the gene names with the probes in the expression data. So we can set the column names of expression data as probes, then match the probes in the expression data with the probes in the annotation data. Before we go ahead to save the gene information files, we can check if the probes' names are the same in the expression data as the annotation data. If we run this code, you can see the return is 0, so all the probes in the expression data match with the probes in the annotation data. So now we can create a gene information data frame as gene information 0 to show the probe's name, gene name, the module color, and the gene significance for each gene, and the p-value for gene significance. So if we have a look at this data frame, you can see we have the probes in the row names, and also the probes name in the first column. We have the gene names here, we have the module color, the gene significance associated with the weight, and the p-value. So now we can reward the module by linear significance for weight. Then add the module membership information into the data. Then we reward the data again, first for the module color, then reward it for the gene significance. So now we can save the gene information for future analysis. So I saved it into my WGCNA folder. Let's open that folder, have a look. You can see we have a G information Excel file here. We can click to open it, have a look at the information inside. So you can see in the column C we have the G information, and in the column E we have all the module color. It is arranged by the alphabetical order, and also the most significant modules are located to the left. For example, the first one you can see is the brown module, next one is the red module, then other modules. Okay, I'm going to stop here for the third part, analysis. I hope my demonstration could help your data analysis. If you haven't subscribed my channel, please click the subscribe button after you watched my video. Thank you, and I hope to see you in my future videos.